There we go. Starting the recording. All right, so we are pretty much done with the first set of operators and discussions with set theory. There'll be more coming later, okay? But we have to talk about functions first in order to get to the other concepts, related to, how to describe the cardinality of a set. So we'll go ahead and move on to functions. And functions, you guys know functions already because you know the math definition of a function, like sine, cosine, log, exponent, and stuff like that. You also know the definition of functions in C and C++. Okay, you write a subroutine, it returns a particular value, it might have parameters and stuff like that. So you already know functions. But in this class, we don't look at functions the same way as most of the math classes. I cannot say all, but most math classes do not view a function as a set. But in this class, we do. So we'll go ahead and start with this portion here. You're trying to launch insecure content from within a secure site. Okay. Fine, we'll click that. And we'll start with this note here. So the first thing we need to do is not even to talk about sets so much, but to talk about tuples. We already talked about tuples when we talk about Cartesian products of two sets, right? So a tuple is basically an array. Okay, it is very close to the concept of an array, where ordering of the value, the ordering of the values is important. It is significant. So when you have a tuple of 1, 1, 2, okay? When we write tuples, we use parentheses and not braces. So when you look at the tuple 1, 1, 2, first of all, you notice that, hey, there are two ones here. When you describe the elements of a set, you cannot have two ones in the same set, because every element in a set is supposed to be unique, has to be distinct. But when you're using tuples, which is kind of like an array or a vector, you can have duplicate values. That's not a problem. So 1, 1, 2 is perfectly okay. But 1, 1, 2 as a tuple is different from the tuple of 1, 2, 1. So even though both of these two tuples have two occurrences of 1 and one occurrence of 2, they are considered different because the ordering of the values are different. So ordering is important when we are talking about tuples. Once again, when you're listing elements inside a set, the order does not matter. Okay? If I use the set notation using braces, ABC is the same thing as CBA, which is the same thing as BAC, and so on. But when you're using parentheses, which means you're dealing with tuples, the ordering is important. Are there any questions? Yes?
For a set, if you had just 1, 2, would that be equal to 1, 1, 2?
You would not have 1, 1, 2 because you cannot list the same element twice in a set. So when you list elements in a set, you cannot have two elements of the same value. So the one value can exist only once as an element in a set. All right. So in this case, ABC is a 3 tuple, because there are 3 elements inside. For the most part of the discussion, at least for today, we're dealing with 2 tuples, okay? Because we only have 2 items inside those tuples. But basically, whenever you're dealing with n elements inside a tuple, you just call it an n tuple. That's just a terminology thing. I'm also borrowing the indexing operator. So assuming that T is a tuple, I'm using T bracket I to indicate, to designate element I within the tuple. It's just like, with arrays, okay? So T bracket I is referring to the element at position I in an array. So I'm just borrowing the operator from programming. And then the last operation we perform on tuples is the bar notation. It just tells you how long or how many items are in a tuple. So we borrow this one from set notation, which is the cardinality. Are there any questions about tuples in general? By themselves, they're not that useful. It's only when we combine tuples with the discussion of functions, then it becomes a really, really important part of our discussion. Is that okay? All right. Okay. So moving on to general discussion of functions. So we learn functions in other math classes, in programming classes, and so on. But in cisp440, functions is an important concept to facilitate the discussion of many other topics. So we'll have one example at the end of this module that makes use of a function. You can define a function in many other classes just like this. F of x is 2x. So you're defining the function this way. So when you plug in specific values, then you can say f of 2 is 4, f of 3 is 6, and so on. Are we still doing okay so far with the discussion of functions? Okay. But in this class, we look at functions more as a map that maps elements from a domain, which is where you the values that you put into the parentheses when you apply a function, to a codomain. The codomain is a set of values that can be outcomes of the function, of the application of the function itself. Okay? In many other classes, the word range is used instead of codomain. They mean exactly the same thing, but in this particular class, I would just consistently use codomain to describe the set containing all the possible values of the outcome of functions. Is that okay so far? Okay, so we have code, we have domain where we get stuff from, and then we map those things to a codomain where we have the result values. So you will see this notation a lot of times in this class, not just when we are only talking about functions, because we use functions to describe other things. So f, in this case, is a function, and x, uppercase x, is the domain, and y, uppercase y, is the codomain. You guys okay? All right.
Had to sign up to my phone.
Sorry?
Had to sign up to my phone.
Oh.
Then he reminded me of something.
Oh, I didn't even hear that. Was it a funny tune or something? Okay. So this is just describing f is a function. It maps elements in x to elements in y. X is our domain, y is our codomain. Okay, moving on. Yep, go ahead.
So in functions here, it doesn't do anything to the domain.
It does not define what the function
is. We already have a codomain set up.
This is just telling you what is the domain and what is the codomain, but it doesn't tell you how it is mapped.
Okay.
So the actual mapping is done in a different way. That's a good question, but we'll get to the actual mapping part. So if we are to define something like this, but using the notation that we will be using in this class, the first thing we need to do is to define, okay, what is the domain of this function? Now in this case, 2x can use a variety of domains. You can use real numbers as a domain, you can use integers as a domain, you can use natural numbers as a domain, you can use complex numbers as a domain. So you have choices, okay? But in this class, because we're dealing with mostly programming concepts, so integers are very important in our discussion in this class. And that's also the reason why this is called discrete structure or discrete math as opposed to continuous math. Because we are dealing with things that are individual, okay, quantized, not continuous like in your calculus class. Okay? So there are no taking the limit of something in this class, because that's a concept that you apply when you're dealing with continuous quantities. But in this class, we're dealing with discrete quantities, so we go like 1, 2, 3, A, B, C, and so on. So in this case, I am going to say that with this particular function, yes. Go
Sorry,
ahead.
I'm just a little confused with the. I know it's a little ways back, but we're talking about the domain versus codomain.
Mm-hmm.
Is that just codomain's just the like the y-axis if we're talking about like a coordinate plane, or
You can look at it that way. You can look at it that way. It's just that when you look at things from the y-axis, it depends on how you define what you're drawing.
Yeah.
Like you can draw a circle, right? But a circle is not a function.
Yeah.
Because given any x, there are two y's.
Yeah, it fails
and given
the
any
vertical
y,
lines.
you have two x, so it's not actually a function.
Mm-hmm.
All right, so in this case, I'm restricting myself and say, okay, I want to define a function that has this property, but I'm restricting myself to use only integers as the domain and only using integers as my codomain. So how do we define that function? How do we spell it out? This is one way to spell it out. Okay, so every element inside a function, so remember, a function is now seen as a set, okay, which is probably unique to this class because none of your other classes would look at a function as a set. So each element of a function in this case is a two-tuple, where the first item of the two-tuple is an element from the domain. The second item in the two-tuple would be the mapped value in the codomain. So together, when we look at the highlighted portion on the projector, it means 0 is mapped to 0. Okay? The left 0 is where we're mapping from. The right 0 is where we're mapping to. And you can probably see how this is really, really verbose. And 1 is mapped to 2 because, after all, f of x is 2x. 2 is mapped to 4, 3 is mapped to 6, and so on. So are we getting a kind of good sense of how we are using the concept of a set of two tuples to define a function? Is that okay? All right? Okay. But obviously, this is not a very good notation. This whole thing is not a very good notation because, well, we have now a question of what about the negative values? Do we map -1 to -2? It's not spelled out here. Now, even if you spell out as much as you can, the ... is always ambiguous because we don't know the exact range. Okay, where do we start? Where do we stop? It's not usually it's not clear about that part. So a much better way to do that is to do it like this. Okay, so let's take a look at this notation here. F is a set, okay, where each element takes in the form of a two-tuple. But each two-tuple has a form of x2x, which means the first item has a particular value. The second item is always twice the value of the first item. The only restriction is x has to be an element of the set of all integers. In other words, x has to be an integer. So this is a quick and easy way to describe the elements of a set that has an infinite number of elements. But we know how the first and the second item relate in a two-tuple. Yes?
What does the pipe symbol mean again?
Such that.
Such that.
Yep. Yep.
So there's just kind of like the format of it. We have the x2x and the set of all integers, so it can be for any value basically. You're saying like it's an infinite set, so we can. Yeah. Oh, okay.
It's just describing properties. Okay. Remember, this really means the next line is probably better. This boils down to this. Okay, it boils down to say that for all x that is an integer, for all y that is an integer, y equals to 2x if and only if xy is an element of f. So they mean exactly the same thing. This notation versus this notation, they both mean the same thing. The second one is a little bit long and a little bit verbose, but it is more spelled out. In other words, if you give me a two-tuple, okay, you give me a two-tuple of 14, 28, okay, I can tell you right away that it is a part of f. It is an element of f because it fits that description. Because when you say that, I give you a two-tuple, 14 and 28, 28 is 2 times 14, okay? As long as this requirement is met, this has to be true, which means 14, 28 in parentheses has to be an element of f. Is that okay? What about 0.5 and 1? Well, with 0.5 and 1, it's not part of our consideration because we are only considering x that can be an integer, y can only be an integer. If x is not an integer, I'm not even considering. This statement does not apply to anything that is not, where x is not an integer or y is not an integer. Yep.
That statement, or what you call that statement? The thing you're highlighting right now, the entire thing, that's a statement, right?
That is a statement, yep.
So it's kind of built in a way where you check in sequence, isn't it? You start with x, because that's the most important, that's the first thing you want to know.
Well, you can, with this particular one, you can flip the x and the y. You can say for all y that is an integer, for all x that is an integer, because all we're doing is delimit the scope. Right.
Or x divided by 2. So you could just flip it and just view it a different way, but yeah.
Right. You can flip that. Or if you really want a shorthand, you can say for all x comma y as elements of z. You know that's another shorthand. Yep.
So that statement kind of defines
That statement kind of.
defines f. in that case.
Yeah. Yeah. So these three are the same. Excuse me. These two, this statement, and this statement are exactly the same thing, except this one is more concise. Yep.
Can you read the second statement?
You mean the for all?
Yeah.
So it says here for all x that is an integer, for all y that is an integer, y equals to 2x if and only if xy as a two-tuple is an element of f. Which is just reading out the mathematical symbols.
Yeah, I just wanted to know if I had it like right in my head.
Oh, okay. That's a good idea. Double check. So are we doing okay so far with this kind of notation? Yep.
So it's the function. The function is the domain and the set of outputs of the domain together. So it's not like the actual formula or the operation I do. It's the domain and the set of its outputs that really defines the function.
So the function is a set of two tuples,
Okay.
where each of the two tuples will map a single element from the domain to a single element in the codomain.
Okay.
Okay, so that's how we look at functions, in this class,
Okay.
is to look at it as a set of two tuples. We do not define the actual formula or the equation unless we're using something like this. So in here, the formula is basically listed here or here. But we are not using the usual traditional way of doing it like this.
Okay.
Now, the reason why we do it like this, using a set notation, is so that we can do arbitrary functions. In other words, it doesn't have to be a mathematical kind of function. We can do all kinds of mapping this way. As long as you tell me what the domain is, what the codomain is, we can do any type of mapping between those two sets.
Okay.
There was a hand earlier back there. Yes, go ahead.
So a function could be of like n tuples though, right?
Yes, it depends on what is in x and what is in y.
But could it be x, y, z? Like, could it be sets of 5 tuples?
You mean each element can each element be a 5-tuple inside the function?
Yeah.
The answer is yes, because it depends on what you're mapping to what. Because you can start with a domain that is already that's already a planar coordinate, and then you can have your range or codomain also being a 2-dimensional coordinate. So now each element is technically still a 2-tuple, except the first of the 2-tuple itself is a 2-tuple, and then the second of the 2-tuple is also a 2-tuple. So you can look at it as a nested tuple, or you can look at the whole thing as a 4-tuple. Yep.
Can it only be mapped to integers?
Nope, it can be anything. Okay, so that's a good idea. So let's go ahead and take a look at some examples. Okay, so we'll take a pause from the class note, from the notes, and then we'll take a look at some examples of functions. Okay, so I can arbitrarily define x to be just a, b, c, and I can define y to be 1, 2. Okay, so they don't even have to have the same number of elements. Okay, x can be more, y can be more. Okay, so either way is fine. Now I use this notation to, well, okay, this is the minus greater than is an approximation of the right arrow, okay, because I can't really type the right arrow with a text editor. So now I'm just saying that with this f here, x is the domain, y is the codomain, okay. But in order to figure out the actual mapping, I can list out all of those, okay. So I can say a is mapped to 2, b is mapped to 1, and c is mapped to 2. That's a function, okay? Because I mapped every single element in the domain to something in the codomain. And you might say, but A and C are both mapped to the same thing in the codomain. That's okay, it's fine, not a problem. Okay, they can map to the same thing. But the key is everything in the domain is mapped to exactly one and only one thing in the codomain. They can map to the same thing. Two things from the domain can map to the same thing in the codomain. That's not a restriction of being a function. Yep.
Does everything in the codomain have to be mapped to?
Nope. That is not required either. So in other words, in this case, another example of a function is this. You can map A to 1, B to 1, C to 1. It is still a function. Is that okay? All right. Any other questions? So it is somewhat arbitrary, right? We can now define a function that has no formula corresponding to it. I mean, why would we map A to 2, B to 1, C to 2? I have no idea. This is just an example. Yep.
You can map A to 1 and 2 as well, right?
That is not okay. So in section 3.1, we'll see what makes a function a function. That's the key idea of each element of the domain has to map to one and only one thing, element in the codomain.
So can you have like a 2-tuple and a 3-tuple in a function? In a set?
Probably not, unless your domain can have both single values and 2 tuples. But typically we don't encounter those situations. All right? Yep.
So if the things in X didn't map to the 2 in the Y, is 2 still a codomain?
2 is still an element of the codomain. The requirement of being a function does not require that everything in the codomain are mapped. You can have like a whole lot of stuff in the codomain that is not touched by the function. That's okay, not a problem.
But
Yep.
so you said X, all the stuff in X, the stuff in the domain has to be used. Though. So if there was
Yes.
A, B1, and then nothing left.
Right. Then it would not be a function. Okay. F would not be a function. It is still a map, but it's not a function anymore. Gotcha. We don't call it a function. Yes. Mm-hmm.
So in a real program, we have to have the sets and everything declared before the function. Is
Yes.
it the same thing in this?
Yes, because in order for us, this particular module does not touch on injection, surjection, and bijection, but in order to qualify whether a function is injective, surjective, or bijective, we need to define both the domain and the codomain before we list out the elements in the set.
So everything has to be in scope? Basically.
Yes. Mm-hmm. So we know at least what the scope is. Mm-hmm. All right, very good questions. Any other questions before we move on to section 3.1? Yes, go ahead.
Do we have to be able to describe it?
To describe
Like in the function notation that you did before, with the, like all elements of X and all, like, I don't know.
Nope, it depends on the context. Sometimes it is not possible. In fact, sometimes we just need to know there exists a function that can map from here to here. We don't even care exactly how it is mapped. We just need to know, does a function exist that can accomplish this mapping? If at least one is done, is possible, we move on. So the way we look at functions in this class is very different from the way you look at functions in your other math classes, where the definition of the function is important, right? This is sine, this is cosine, this is logarithmic, this is exponent, and so on and so forth. So they start with the definition of the function of how things are mapped. In this class, sometimes we care, and other times we just go like, okay, there has to be a particular bijective function to map these things to this thing. As long as there exists at least one function that can do this, we are cool. Okay? So, because we are not mapping things that are mathematical, we are not mapping values based on functions that model reality stuff, okay? Because sine and cosine are reality functions, okay? Because when you rotate a ball, the x and the y coordinates change in a sine and a cosine way, okay? But in this class, we are talking about indexes of an array, okay? So when you look at, okay, this is a preview of what we'll be talking about later today, but I think this is the right context. So when you look at a sorting algorithm, okay, You are given some initial values in an array, potentially not sorted, right? And then you look at the outcome of a sorting algorithm. Well, you should be able to find a function to map the index of an initial value to the outcome that is 1 to 1. So everything that you start off with should exist at the end. So we'll get to that later on today, and we'll also continue with that idea next Monday. Okay, but this is one of the reasons why we use functions in this class. All right, so moving on to talk about what makes a function a function. So the first thing is, okay, this is actually incorrect because this really should be a subset of, but not a proper subset of. So I need to change this. So let me fix that first. Okay. And this one is 0 to 9. Okay, what makes a function a function? So this is subset EQ. There we go. There we go, fixed. So F as a set has to be a subset, not necessarily a proper subset, of X being the domain, Cartesian product with Y, which is the codomain. That kind of makes sense, right? This is how we come up with all the two tuples. The Cartesian product is what can generate the two tuples. But at the same time, F most likely is not going to use all of the two tuples generated by the Cartesian product. Okay, there's only one case where okay, the original version is to use the proper subset of. This is just subset of. There's only one case where it really makes a difference. The only case where it makes a difference is when X is a singleton.
Is it what?
Is a singleton set, which means the set only has one item, has one single element. So when X only has one element and Y only has one element, then the other one, before I corrected this, would be wrong. Because what is the one set that is a proper subset of a set of only one element?
Empty set.
The empty set, exactly. But the function does exist. If you have one thing in the domain and one thing in the codomain, can you make a function out of these two? There's only one possible function that you can make out of this, because you only got one thing in the domain, you only got one thing in the codomain, so the only element in the function is going to map the only one element in the domain to the only one element in the codomain. But that's also just the Cartesian product itself. So that's why I have to change the subset of, the proper subset of, to just subset of, to account for that one special case where X and Y only have one single element. For all of the other cases, subset of, proper subset of is fine. Okay? All right. So in addition to this observation, where F is a subset of the Cartesian product between the domain and the codomain of a function, we have the following requirement. Okay, so I'm going to highlight the English version of this statement first. Each element of the domain must be mapped to one and only one element in the codomain. Okay? It's fine. I mean, it looks like it makes sense, and it seems like most of us would understand what this means. But remember, natural languages are ambiguous. Okay, there's always some room to be interpreted incorrectly, or in different ways. Okay, I'm not going to say incorrectly because sometimes there are just multiple ways of interpreting the same thing. So the question now is, can we re-express this in a different way? So what is going on between here and all the way down to here is really just my way of showing you, how do I come up with the long expression. Okay, so I'm not going to go through that process in the class, but you should read about it just so that you understand how to generate or how to come up with mathematical notations of something that you otherwise can write out as English statements. Okay, so I'm not going to repeat all that stuff. So I'm going to jump all the way to the result of all of this reasoning, and go like, okay, let's take a look at this big, huge mess here, and try to figure out what does that mean. Okay, so what are you going to do when you are presented with a statement like this, and go, okay, make sense out of this? What are you going to do? You read it step by step, right? When you encounter symbols that you do not understand, you look up that symbol and go like, okay, what does that mean? All right, so we start off with this. It says for all, okay? Which is also the same thing as every, okay? So it's basically saying every. It's basically saying for every element E that you can find in the domain. So right at this point, okay, this is the first thing you have to do first, is you're binding E to a particular element in X, and say that no matter which element I bind E to, the following has to be true. Is that okay? If it is a derexist, if it is a mirror image of the E, then it really means, you know, you just have to find one, okay? Then the whole statement is true. But this one is saying no matter which element in X or the domain you bind E to, the following has to be true. Is that okay? All right? Okay, what has to be true? Okay, let's figure this out. So what has to be true is this huge mess here. So whenever you read an expression like this, you read from the outside in or you read from the inside out, but you'll have a consistent way of doing it. So in this case, I'm going to do it from the outside in, okay? So what is the outermost operator of this entire mess? The equal to. The equal to is the last thing that you do. It's comparing, okay? So we are comparing something against something else. Let's start with the easy one. What is on the right-hand side? What am I comparing to?
1.
The constant of 1. Okay, cool. What am I comparing from? This whole mess here, right? Okay, all right. So we are getting into the detail a little bit more now. So at this point, we understand that it's saying no matter what element in the domain you bind E to, blah, 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 equals 1. Okay, so what is blah, 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 blah? Okay, so you look at the outermost portion first, okay? You know, it looks complicated, but you deal with it one level at a time. So when you deal with it one level at a time, the outermost portion would be a bar and a bar. What does that mean? Cardinality, or the number of elements in a set. Okay? Is that okay? All right? So we are counting the number of elements in a particular set, and sets basically we're saying, okay, this set must have exactly one element. That's what we are asking for. But what exactly is that set? How are we constraining things, or what elements should be in this set or not? This is it. Okay? All right. So what this notation is saying is, for each element in this set, it has to be a 2-tuple. Okay? So each element of the set is a 2-tuple, with the first item being P, the second item being Q. But we're also going to add some additional constraint to what can be in this set. So the additional constraint is P has to be the same as E. The first item of the 2-tuple has to be the same as E, which is already bound to a particular element in the domain at this point.
So it's saying it's an element in X.
It's an element of the domain.
But it's not just any element in X, it is the same as E, which is already set. A particular thing. We know it is a particular thing in X.
Okay.
Okay? What about the second one? This is a conjunction. Okay? It's an AND. And the second one is saying PQ has to be in F.
Has to be part of the function.
Hmm?
Has to be a valid function. If it's x2x, it has to be p2p.
Well, we're trying to evaluate whether F is a function or not, but F is already a set of 2 tuples. So I'm saying that, we are trying to count the number of elements in F, where the first item is E. Okay, I'm not putting any constraint on the second item. There's no restriction of what Q can be. I'm just putting a constraint on P, which is the first item. Okay? Yep.
So it's saying P is X, or
It is saying P is E.
and
E is
element.
E is already bound to a particular thing in the domain. Is that okay?
So
Yep.
X means domain.
X in this case means domain. X comes from the notation earlier. I'll get to that. Just hold a second. So X comes from all the way up here. So all the way up here, we already specified that X is the domain.
So if they ever use X or Y, we can assume that it's domain and codomain.
No, you have to tell me this. You basically have to spell this out first. Then whatever you use at this place is your domain. Whatever you use at this place is your codomain. Yep. Question?
Would the P and Q be the only element in F?
Not necessarily.
Not necessarily.
Yep. Because what I'm restricting here is for a particular thing in X that I call E, so that I can refer to that thing that I'm focusing on right now. I'm trying to create a set. This is okay. For those of you who know what is SQL, this is an ad hoc query. Okay, so we are creating a set on the fly without giving it a name. Okay, so now we want to say, okay, but what is in this particular set? This particular set has two tuples, because this says everything in this set has to fit into this particular form. But what other constraints are we going to put? Because if it's just a set of possible two tuples, it can be, the first one can be a card that I like, the second one can be a card that George likes, right? Otherwise, because there's no restrictions at this point. So the vertical bar right next to it is saying such that, so that we can put some constraints on what these two things can be. Okay, what can be P, what can be Q. So the first one says P has to be equal to E, but E is already bound to something in X already. So this is basically saying P is an element of the domain, a particular thing in the domain. And then on top of that, yep.
So you could have gotten rid of the P equals E by just putting E in the first part?
I suppose you can put E over here and then change this to E and then get rid of this.
Okay.
Yep. So the second constraint, on the other hand, is saying PQ. Okay, I'm not saying what Q can be. So Q is what we call a free variable. It is not bound to any particular thing. So if you can find, E something in F, it belongs to this set. If there are 20 gazillion things that start with E in F, they all belong to this set. Yep.
Q would be something in the codomain, though, right?
Q would be in the codomain, correct.
It has to be.
Yeah, it has to be because PQ is an element of F. So if this requirement is met, if you look at this entire thing, if you can say, I have examined everything in the domain, and for everything in the domain, it only maps to exactly one thing in the codomain, then F is a function. Is that okay or not?
So so the cardinality has to be 1. So can there only be one P and Q?
Only one P.
Only one P.
There's only one thing that P or E maps to.
Yeah.
Okay.
But it cannot be 0, cannot be more than 1.
Yeah.
Okay? Yep.
So can you read the first part, the E and then the E to the X? Like the actual first part.
The first part is to bind E to a particular thing in the domain. Okay, so maybe if I use pseudo C code would be helpful. Okay, so I'm going to put a pseudo C code here. Okay, so I'm going to put this up all the way to the top, and I will leave some space here so I can use this to write some C code. But it's going to look kind of funky, okay, because it's C doesn't have the innate ability to deal with getting elements of a set. So this is kind of like a mixture of what you already know. And can I use this? How many people are familiar with the for each? statement in various scripting languages. Okay, there are some, but not everybody. Okay. Okay. I'm trying to find out, how to do this.
Isn't it just a for loop with like unimax, and you start with
I know what to do now. For E equals to first thing in universe. Okay. And then the condition to stay in is we have not exhausted everything in universe. E is the next thing in universe. Okay. In other words, this is a loop. Your usual way of using a for loop is for I equals to where you want to start, I is less than one more than where you want to end, plus I to move on to the next value, right? So I is only representing a particular value that is of interest to you for each iteration of the for loop. That's the usual way of using a for loop. I'm borrowing that concept, except I'm enumerating everything in the entire universe and say, this is the first thing, that's the last thing, okay? How I sort these things is not important. The key is I have a way to get to the next thing in the universe and keep going until I have exhausted everything in the entire universe. Is that okay? All right. Remember, this notation is really just saying E is an element of X implies the following, right? So we can now say, okay, so I need another variable up here. Okay. Statement truth. There we go. So we're going to initialize statement truth to a particular state. So we'll just initialize this to true. In other words, we are optimistic that the statement is true to begin with until we find something contrary to that. We are just going to say the statement is true. Okay? So we'll put a 1 here. Okay? Now the best way to specify true in C particularly, because C has no Boolean types, is just to say it is not false. Because we don't know exactly internally what it wants to use, as quote unquote true.
Oh, because it's hitting them.
Because anything other than 0 is true. So so just so that we don't over specify, oh, 1 is true or -1 is true. It's best to say it's just not false. Whatever it is, it's not false. Okay, but it's just a little quirky thing. Yep.
Would it need a type?
Huh?
Would it need a
Fine. Okay. All right. So now in the loop here, we can say statement truth is statement truth and the following. Is that okay so far? In other words, for each iteration of the loop, I'm just looking at the statement truth up to this point, and the statement, whatever I'm going to evaluate here, is going to be conjunction with whatever that I have already. And that is because the original statement is a for all. In other words, if I can find one thing in the domain that makes this statement false, the whole thing is false, because I cannot assert that it applies to everything in the domain. Is that okay? Does everybody understand why I'm using the conjunction here, the ampersand, instead of the or? Yep.
How could it become true then?
Huh?
Can it become true in this?
It's true to begin with.
Okay.
Statement
Yeah,
truth
yeah,
has an
yeah.
initial value of true,
Yeah.
because true is not false.
Yeah.
Okay, so the next question is, okay, so what is this thing that we want to check? This is top-down design. I don't want to spell out everything here because it's going to mess up the whole thing. So I'm just going to say px. In other words, I look at this whole thing. Okay, I should start here. I look at this whole thing and say, that's P of x. It's a predicate. It's a function that returns either true or false. Is that okay? Yes? No? Kind of? Okay? All right. Okay. So now I say, okay, since P of x is a predicate, x has no particular type because it can be anything in the universe. So if you really want to have a type for x, it is a thing. I don't know what it is. It can be a floating point number, can be a car, can be a person, can be an element, can be a subatomic particle. I have no idea what it is. Okay, so it is just a thing. But that's okay, because the first thing I'm going to do is to say, if it is not an element of the domain, just return true. Okay? So I'm going to use a very bad programming practice here, but since everybody knows this one, I'm going to use it. Okay? So if it is not the case that x is in, I probably should not use x here. This is E. This is supposed to be E, so we'll go ahead and use E here. Sorry about that. So if E is not in our domain X, okay, fine, we'll pass that as a parameter too, because I don't like to use global variables. And domain X is a set, right? Remember, this is pseudo C, okay? It's not exactly C. Return true. Does that make sense to you? Because the original statement says E is in X implies the following. But implication is basically saying if the first part of the implication is false, the whole implication is true. So if E is not in X, which is what I'm interested in, just say true. Okay? In other words, does this apply to E when E is a Miata? Yeah, fine. We don't care. It does not even matter when E is not an element of the domain. Okay? If it's just something else, just say true. Okay, so the else is where things is interesting. Now this else is technically not needed because we have a return inside the then branch. So technically, whatever follows is going to be the entire else branch, okay? But, just from the perspective of writing code in the right way, you really should be using else. Okay, so else is corresponding to, okay, now that we know E is an element of the domain, what are we looking for? Is that okay? Okay. So in here, we'll use a counter. Okay, so we say counter or cardinality. Okay, use the proper words. Cardinality equals to 0 because we want to count, and we also want the loop to do some counting here. So we'll say for. And this time we have P. Okay. So P is another thing. P is first thing in F. Whoops, nope. No. Okay. No, it's PQ. PQ is first thing in F. Okay? Would that be okay? Because F is a set, so I can, I can find a way to enumerate and go like, okay, if I need to list all the elements in F, this is the first one I'm going to get. Just to do it properly, everything, there are no globals. Okay. And to stay in this loop means, have not exhausted everything in F. And then the next one is PQ is the next thing in F. Is that okay? In other words, this loop is just helping me to evaluate everything in F. Because everything in F is a two-tuple, I'm automatically fitting each thing in F into the two individual items P and Q. P being an element from X, Q being an element in Y. One is from the domain, one is from the codomain. Is that okay? All right? So now we can do some counting. And what do I do here to increment cardinality? In other words, what is counted as a part of this ad hoc set? What do I put here? Look at the mathematical notation at the top. And so where are we here? We already took care of PQ is an element of F, okay? Just because of the way we set up the loop, everything, all the PQ in parentheses are elements of F already. So we got that taken care of. What is the other requirement? P has to be the same as E. E is a parameter that is passed to me. P is a local variable that we use for the loop. So, oops, like that. Is that okay?
Double equals.
Oh, double equal. You guys got me. Okay, very good. I was counting on GCC to catch it. And it would. Actually, GCC has the ability to catch stuff like that, but only if you turn on all the warnings. So if you say GCC or G++ dash uppercase W, lowercase ALL, it would actually catch stuff like that. It would tell you that, hey, this potentially is a problem. But only as a warning, where most people just ignore it. Oh, it's a warning, it's cool, it's fine. Okay, so but are we doing okay so far with this code here? Pseudo C code. All right, so by the time, okay, let me see if I can zoom out a little bit here. There we go. Okay, but at this point, we're only tracking a cardinality. We are bumping it up by 1 every single time we find a tuple in F, such that the first element is E, okay? What are we doing with that cardinality? We want to compare that to something at some point, right? So if we are to specify a return statement here, which is also very, very poor practice, because we have a return statement inside a branch in a conditional statement. But just for the clarity of this code, this is okay, okay? So what are we going to return as the value of P of X, which is the predicate? What are we comparing the cardinality to? 1. Very good. So we are saying when cardinality is 1, return true. So now I have turned this thing here into a pseudocode that does about the same thing. Yep, go ahead.
Do you want to return false? Because if cardinality is true, then your statement isn't true.
It will continue to stay true until we find something in the domain that doesn't meet this requirement.
It's going to go through the loop, but that's going to have
Yep.
for cardinality.
Yep, go ahead.
You said if not E and X, so that's saying if E is not an element of X, return true?
Correct.
But isn't E supposed to be an element of X?
Not yet. Because the way we set up E can be anything in the entire universe. So you look at the bazillion things in the entire universe and you go like, I'm going to look at these things one by one. And that one by one thing, because you can only look at one thing at a time, that one thing that you're looking at is E.
And it's not in the domain.
If it's not in the domain that we're interested in, we just say not interested.
Kind of like the implication.
Yep. We just say, so by returning true, right away, we're simply saying not interested. But if it is an element of the domain that is of interest to us, then we go through the else branch and go like, now we are interested. We want to check certain things. Okay? Is that helping? Sort of? Yep.
In order for the function's is it the function's cardinality? Is what it is? In your
The cardinality?
statement. That's for a function, right? Cardinality is used to describe the number
The
of
cardinality
function.
here is not for the function itself. It is for the ad hoc set that we are dealing with here. That is it is trying to calculate the cardinality of that set. But instead of constructing the set and then counting the element, I'm just counting how many things are actually in the set. Okay? All right.
Can I see the code you wrote? Can I see that? Okay.
Yep. I think zoom out a little bit may help because it gives us a broader view of the code even though the font is going to be smaller. Is that okay or not? This is the first time I use a pseudo C code to explain the for all thing.
So this will exit if you either have no matching or have two matching. So domain matching with two codomains.
Correct. Yes. So if you have something in the domain that does not map to anything in the codomain, it will make this cardinality a 0. And then when cardinality equals 1 is false, it goes back to the previous one, and that will turn statement truth to false. But once statement false is false, it can never become true again, because all the other things are conjunction with it. So once it is false, it latches, and it won't become true again. Now you can do you can short circuit it a little bit. For those of you who are after efficiency, you can always say, you can say, statement truth and end that. Okay. In other words, when statement truth becomes false, you just exit right away because there's no way to turn it back to true again. But that's just optimization. It's not needed. Yep.
Do you have anything that deals with cardinality being over 1?
Yes. Cardinality can be more than 1 because after all, there can be multiple things in the set that has a particular element of the domain as the first item, right? So in that case, this statement would execute more than once, which means cardinality equals 1 is going to be false. Then it goes back and turns statement truth to false. Now, whether you optimize or not, statement truth will never become true again. So now we say, oh no, that's not a function because f as a set of 2 tuples does not meet this requirement. Yep. Mm-hmm.
So if it returns 1 a second time, it'll break it. How does that happen?
If it returns,
so if p equals e and the cardinality increases to 1.
1 is exactly what we want.
Is more than 1.
If it's more than 1, then it will become false.
How?
Okay, let me do one thing first, and then go ahead.
For total clarification, in order for cardinality to be 1 for a set, for this set, there can only be 1 value in the domain, and then the codomain can have as many as you want. Isn't that true?
Correct.
Okay.
So I'll give you some examples. Just let me finish the declaration of this whole thing, just so that we know what is the context of this code here. Okay? So this code here is really just the overall code to check to see if a given set of 2 tuples f is a function or not. Can it be called a function? Okay? So to be very, very clear, we will say that this is a set of 2 tuples. That's what f is. And x is its domain. Okay, so x is just a set. Is that okay? Okay, I can upload this to Canvas so that you guys can look at this and get more confused.
Would appreciate it.
Yeah, that'd be great.
Okay. So let me save it first. If I don't remember to upload, at least I have a local version of that. So let me save it to, how should I call this? Is f a function? Sounds appropriate?
Biotank adventures. Biotank adventures.
Say again?
You make a game.
Make a game?
I saw Biotank adventures.
Oh. Oh, right, upload it. All right, so we'll go ahead and upload it to this module. I can do this really fast in Moodle, but this is a little bit different. New file. There we go. And it was called what again?
Is F a function?
Is F a function?
Yeah,
F is a function.
Yeah,
F,
it was right there.
Right there.
huh?
Nope. Yeah.
Oh,
It
is
was
F.
Before you searched it,
It was a dot text.
There we
Right
go.
there.
Yep.
There we go. Okay. Do not indent. Okay, cool. Add file. There you go. So now you have the text file that I just created uploaded. Usually I don't upload the scratchpad thing because the lecture is getting recorded. It's not needed. But since this one is kind of long and it's kind of complicated, you might want to look at it again. So that's why I uploaded. Is that okay? So I'm converting a mathematical notation to a sequential way of evaluating it in the form that programming people should understand. Okay, but that's a crutch. Okay, so eventually I don't want you guys to be thinking about for loops and stuff like that. Eventually I want you guys just to read the notation in mathematical notation and understand what it means. But at this point, because it is new to us, this is a good way to bridge what you already understand in cisp440 and all the other previous classes, and bridge it to something that is kind of new, but it relates to what you already know. Is that okay? All right. Very good. Now, we can go back and look at some examples. So what is a function? What is not a function, right? So I now say that f is a mapping. So x is the domain. Y is the codomain. And I'll use very specific examples here. So this is ABC, and Y is 1, 2, 3, 4, like so. And I'm going to evaluate, I will ask you whether this f is a function or not, okay? So this is A1, B1, C1. Is this f a function using x as the domain and y as the codomain?
Yes.
Yeah.
It is, okay? Because for each element in x, it maps to exactly one and only one thing in the codomain. But they're not distinct. They're all mapping to the same thing. It's okay. There's no requirement that they have to map to different things in the codomain. So that's cool. Okay, next one. This is a set. Let's see. Would that be a function?
No.
Why is it not a function?
You're not using all the elements in the domain.
Right. So in the code, by the time E is bound to C, the function P will return false, because there's nothing in F that mentions how C should be mapped. So cardinality would be 0. So cardinality equals 1 at the end of P is going to return a false. The false gets back to the top level function. So now you have a n false, and then the statement truth variable will now latch to the false value. It will never become true again. All right, very good. Let's look at the next one. How about this one? Is that a function? It is not a function, but how did it fail the test?
The domain is used one. Element of the domain.
A is used more than once, but exactly how did it fail in the algorithm itself? Let me switch back to the algorithm.
Maps to more than one element of the codomain.
So cardinality equal to instead of.
Yep, exactly. So that's exactly what it is, because in this loop here, cardinality plus plus would have executed twice, because you can find two things in F that start with 1. So cardinality is incremented twice, which means cardinality will end up with a value of 2. 2 equals 1 is false. That value is getting back to here. And since it is conjunctioned with whatever is the current value of statement truth, it will turn statement truth to false. But once statement truth is false, it can never become true again. Okay, so I want you to kind of think in those terms, because this way you're reading the code and you're figuring out oh, so when we run this code using those examples, this is why it is not a function, okay? Not just that it's not a function, because yeah, I know tag, the first one is, the second one is not, the third one is not. Okay, I want you to know exactly why it is not a function. Okay. Is that working so far with this kind of analogy? Okay, very good. So we'll go back to the notes. So the next one, this slide here is intended as the end of this particular module, which is not necessarily the end of this lecture. Why is the concept of a function like this useful? So the idea is, how do you write in mathematical notation and say that, oh, this is the proper behavior of a sorting algorithm? In other words, you can submit your the initial state and the final state to a function. And the function's job is to say, okay, I'm going to evaluate based on the initial and the final condition of running this particular algorithm. And I can tell you whether this algorithm is doing the sorting job correctly or not. Why is that important?
So the algorithm doesn't work, it's useless.
So say that one more time.
If the algorithm doesn't actually work, it's useless.
Okay, so you can at least tell whether the algorithm works or not. Okay, very good. But why do we want to express it in a mathematical way?
Because you can prove that what you're proving is right.
Aha, I like that word, proof. Okay, go ahead.
Oh, I was just going to say it's easier to communicate to a computer in terms of math instead of words.
So it's more accurate, it's more precise, and usually it's more concise as well. Okay, very good.
To prove that it works in every case?
Sorry?
To prove that it works in every case?
Exactly, so I like that word again, proof. Yep.
So like that's what they did for one of the big things that they just recently solved. They someone submit like a 50-page proof, but they had to put it in terms that the computer can understand so they can actually prove it to people.
Okay, so the computer is actually doing the proof.
Yeah.
Because it's a long, complicated, tedious proof. Okay, very good. So I like all of those answers, because the bottom line is, if I can express a statement that describes the correct outcome of a particular algorithm, then I have a way to describe to a computer program and say, go ahead and analyze that function. This is supposed to be the outcome of that function. And I want the computer not to run test cases, not to throw darts at it, but I want the computer to mathematically prove that this algorithm is correct. What is the difference? What is the difference between throwing test cases, which is what you typically do with your homework assignment to check whether something is right or not, as opposed to mathematically proving that this algorithm is correct? Go ahead.
One is just test cases. It might not actually be whatever was put in. Whatever the function is might not actually ever be correct, because it's just test statements that are going into it, and it's not actually, like, there is no like base grounding of it to actually have been true or to be true.
So when you are testing with test cases, you can miss, right? You can basically use only test cases where it would be successful, but if your algorithm is actually incorrect, the cases where it will not work correctly, you might miss those test cases. You may not even think about testing your algorithm using those particular test cases. Okay, very good. Yep.
Test cases could have extra things in testing, is basically how you find the correct mathematical thing. Like you test and you see which variables are relevant, and then you refine it down to purely the correct mathematical thing that is free of error, so that you don't make any errors.
Okay. So the bottom line is, when you prove something, it is universal. Okay, if you use rigorous mathematical proof, step by step, and you say, okay, this algorithm is going to do this, okay, and then you match that, okay, what the algorithm is going to do, and it matches the desirable outcome. If that matches, you don't have to throw a single test case at the algorithm, because it's going to work for all possible input cases, which is great, because now there's no chance you can miss that one test case that is going to break your program. Okay? This is used to be called, this is people used to call this the holy grail of software engineering. It's called automated program verification. There are many names, but that's one of them. And it used to be called the holy grail because of what? Why would you call something the holy grail? Now, I'm not being religious here. I'm just borrowing that term to mean its usual meaning. Okay, yeah.
It's the end solution.
Huh?
It's the end solution.
It's the end solution, but why is it not just called the solution? Why is it called the holy grail?
Because then you could understand everything and never be wrong. You could create the correct equation for all systems in the world and never have any errors.
Yeah, well, that's nice. That's the property. That's why we like to be able to do these proofs. But why is this called the holy grail? When people say the holy grail, what is it? Usually, what is the implication? Yep.
Everybody wants it, but it's very hard to achieve.
It's very hard to achieve, or close to impossible to achieve. Okay, that's exactly why it is called the holy grail, because it is impossible to achieve. Because back in the old days, when people had these ideas of having a computer to look at a program and prove what the program is going to do, computation power was not abundant. Okay, we're talking about mini computers, computers about the size of a small refrigerator, with less processing power than my watch. Okay, and computers were not networked. Okay, so there's no way to cluster and say, oh, we'll just have thousands of computers to crunch away, to solve a problem. Nope, they're not even connected. Okay, the only way for a virus to spread in those days is to use floppy disks. And you can probably imagine how fast viruses can spread, using floppy disks. How fast can you make a copy and put a floppy disk into another computer? That's your limiting factor. You cannot do that with a floppy disk, because if you drop the floppy disk somewhere without a protective sleeve, it's going to scratch up and you lose the content, in this case your virus. So please be careful with your virus, because because it might disappear very quickly if you don't take good care of it. Okay, so that's the good old days. Okay, if viruses cannot spread that quickly, it means we don't have enough computation power. So people tried already back in those days to try to automate theorem proving by by analyzing a program, but it was not practical because we just did not have the kind of computation power that is needed. But that idea came back recently. Okay, so in the past, I would say 2 or 3 years. Okay, there have been a lot of interest in automated theorem proving, in particular applied to program verification. Why is that the case? What changed? From the 60s, fast forwarding to 2017.
Computing power?
Computation power, okay, so that makes it possible. Just because something is possible now doesn't mean it's needed. Yep.
It's cheaper than dirt.
It's cheaper than dirt, but that's just the availability of the resources necessary to do it. But what makes it necessary now? What makes people go back in time and go like, oh, that was a good idea. We can do it now. Let's do it.
Doesn't it make the program pretty much invulnerable to attack?
Yes, but why is that important?
Because you mathematically proven every input.
Yeah, but back in the good old days, that's important too. But why is it particularly important now? Security.
Everything on the web?
Computer security, exactly. So if you want to look it up, you can look up program verification, computer security, and there are recent articles that talk about this. Okay, I can't find exactly the article that I found recently, like within a year or so. But people are now applying this kind of technique to at least the very, very core part of operating systems. You cannot do this to Microsoft Word because Microsoft Word is a huge program and it has a lot of user interface stuff to it, so it's really hard to test. But what about that TCP/IP engine of a particular operating system? That's a very confined piece inside an operating system. It is very important, right? And it is well defined because TCP/IP is a published protocol. You can quantify, in qualify, you can actually say, this is correct, that is not. Okay? So people are already starting to apply automated program verification to core parts of an operating system. Okay? Do you guys still remember Heartbleed?
Oh yeah.
Okay, and how did that come about?
Oh, that was the hack of the HTTPS or something?
It's the SSL engine that leaks out stuff that is bad.
It was an issue since XP, right? Because it just recently came to life.
Sorry?
It was an issue. It's been an issue since XP, but it just recently came to life, right?
The Heartbleed problem?
Yeah.
The Heartbleed problem has to do with the SSL engine of open source code. So it's not XP, it's not Windows specific.
Yeah, but it's been around since that, right?
It has been around for a while, but then people figure out how to do it. So they can basically send a crafted request to an SSL engine, and then the request will reply, the server will reply with a chunk of its internal memory. Okay, well, it's somewhat random, but if you do it enough times, you might get something useful, like the passwords or some other really, really important stuff that the computer has stored, the program has stored in its memory. And it all happens because, most likely it has to do with string copy and that sort of thing, because it can lead to a stack overflow or heap overflow exploit. You can read the rest, I'm pretty sure it's well documented now, how it happens. But the point is, if automated program verification was applied, most likely this is not going to happen. Okay? Have I shown you the live attack, global, cyber attack picture? No? Okay. So I'll show you this. Norse Corp. There we go. Okay. This is supposed to be live, so every single quote-unquote projectile represents an attack from a particular origin to a particular destination.
Is that Seattle, the top left?
Yeah, it is.
Microsoft.
Seattle has Microsoft, it also has Amazon.
Oh.
Yeah, don't forget about Amazon. Amazon is now the biggest corporation around the Seattle area. It's bigger than Microsoft now.
Is that where they keep those? Is that where they keep those servers for the AWS?
AWS. No, AWS has multiple locations.
Oh wow.
Yeah, yeah. And I think this is only a fraction of what is really going on. I cannot imagine the traffic being this dull.
Yeah.
Yeah.
This is really dull.
They fixed
Okay.
Florida just attacked California.
They fixed
Probably
the
exponentially worse.
Hacked by different roads.
Yeah, constantly. Okay. So when people say, are we worried about ICBMs and nuclear warheads? Well, maybe to a certain extent, but this sort of thing happens 24/7, 365.
What is he?
Okay, and the only required hardware, the only required capital investment to do something like this is a computer that is connected to the internet. You don't even need a super duper high speed connection or super duper computer to do this. Okay, you can be in a cafe somewhere in Thailand with a tablet. Okay, and hackers can do this already.
Do the different colors represent anything, or?
That's a good question.
No one's hacking it.
I'm trying to see if it
Africa's
has a.
pretty safe.
Well, I'm pretty sure they select.
I mean, except for like North.
Yeah.
Hey, this part is all clean right there. Is that Greenland?
That's green.
Yeah, Greenland is, except Greenland is not green, right?
It's icy. Yeah.
Well, it's going to be green very soon.
Yeah.
And with new trade routes to trade with all that green stuff too, so all the crops we've grown, in Greenland, and we'll have, big
Desert.
ships to get all the crops from there, right? Yep. Yep.
So what does this map actually show?
It's showing all the attacks I'm trying to find the key to all of these things. I cannot seem to locate it.
Or you
Yeah, how does it know?
Hmm?
Is there any way they know?
They know because a lot of servers actually has automated defensive mechanisms. They can identify certain attack patterns automatically. So once they identify, they will send those reports to a particular centralized database. So I'm suspecting this is just tapping that particular database.
Yeah.
Yep.
Well, Norse is a security company.
Yeah.
And these are a lot of their honeypots.
Okay.
So they track the information when someone tries to attack one of their honeypots.
In other words, this is only a small fraction of what is really going on.
There were just like 5 that went to Australia exactly the same time.
Yeah, it's funny to watch it. You'll sometimes just see like Dubai or someone get hit from everywhere.
Yeah.
All over the world.
Yep. And don't forget, these are the known attack vectors too. 0-day exploits is not going to show up here. Those are the important ones, but they won't show up here.
We remember that we don't have class Monday, but today you mentioned, I don't know if you said anything for the class with that.
Sorry?
I don't know if you